Thanks all for having me at this ICAA2020 meeting and letting me into your virtual world to chat a little bit about corrosion of aluminium alloys. I also convey this message on behalf of my co-author Mohsen. Look, I dislike this format as much as I suspect all of you do, so please, pretty please, reach out for anything at any time. My hope is the lack of friendships that would have been made at the conference can hopefully be countered by new virtual friendships. Look, I always like to commence my presentations by acknowledging the traditional owners of the land on which I work and live, which are the indigenous Wurundjeri people, and I pay my respects to their elders past and present. The work I'll present today is from numerous students and researchers over the years, but in particular the work of Shravan, Mike and Umaima is presented, and I also acknowledge some collaborators and sponsors that I've been lucky enough to work with. Even as far back as the development of duralumin, a little over 100 years ago now, we see that corrosion was raised in an issue. So here we are, 117 years later, still talking about corrosion. By way of superfast review, it wasn't really until about 1990, which sounds recent but is actually 30 years ago now, when microstructure corrosion relationships really started being quantified, and in part due to advanced characterization emerging. Here's an example of that, an early study from Rudy Buckite. Now, shortly after that study, Rudy also revealed an important phenomenon, namely the de-alloying of S-phase in 2000 series aluminium, copper, magnesium alloys. This revelation was actually a direct function of the advent of a step change in scanning electron microscopy and the resolution that came from field emission gun electron sources. What we see here in these images is copper redistribution and incongruent dissolution of a microstructural feature, which is S-phase. Indeed, throughout the 90s, traction also emerged for the so-called deconstruction approach of understanding corrosion of complex alloys, such as high-strength aluminium alloys, by understanding the electrochemistry of their many phases. And this has become somewhat of a gold standard now, giving rise to a field known as corrosion metallurgy. This is an example of pitting on aluminium alloy 7075T6, where we see a morphology of corrosion that we now know is deterministic and quantifiable in terms of morphology and evolution, allowing things such as structural integrity prognosis to emerge. So what I wanted to do today was spend maybe a minute or two on each of the advances that's come from each new era of relative recent advances in electron microscopy, and then walk through some examples before elaborating and wrapping up. So look, going back some time now, with the advent of EBSD, electron backscatter diffraction, it was possible to turbocharge the characterization of manufactured intermetallics, which are not single crystals, but had to be made as polycrystals in a messy, so to speak, matrix. So by being able to use EBSD to do surface phase ID in a way that can't be done with X-ray diffraction, the electrochemical microcell allowed us to unravel the behavior of nearly all intermetallics in aluminium alloys to date, and an example is shown here on the right for a number of the key intermetallics that populate 7075 in that example. So first order determinism allows an electrochemical classification of the role of microstructural features and their subsequent influence on corrosion morphology. Alright, so look, scanning TEM, which allowed, in a digitized manner, also allowed for images to be obtained at very high magnification and with compositional contrast. Here we see an example of a model aluminium copper magnesium alloy with S-phase precipitates. Following exposure of the TEM foil that we saw in the previous image to sodium chloride for a very short amount of time, so we're talking some tens of seconds here, it was shown that de-alloying that we mentioned earlier could occur at the finest of length scales measured at the time, and that was able to also be analysed by energy dispersive X-ray spectroscopy, and so it looks like little stuff de-alloys too, which we now know. In terms of advances in high-resolution scanning TEM, inclusive of aberration correction microscopes, such microscopy was utilized to assess the microstructural origins of what happens to a microstructure when the rate of pitting, and here it's on this image you see it's being measured electrochemically using the potentiostatic method for electrochemical analysis of metastable pits. So when pitting goes from a very low rate to jumping more than 3 orders of magnitude when we age and go from a solutionized alloy to an aged alloy. So what happens to the microstructure to have this jump? And you can see the red data points there that correspond to a 200 degree heat treatment, and you see that jump. That jump is brought on earlier than it would be for the 150 degree heat treatment. So the result actually shocked us, and these are great aberration corrected STEM images, by the way, that show the difference on the left between a pitting immune microstructure and on the right a pitting prone microstructure. And it was a subtle change in the width of a precipitate that led to that jump. So an attempt to reveal this phenomenology is given by this schematic as well, where it's proposed that a protective surface oxide may be able to bridge precipitates, provided they are less than a critical size, which is around about 5 nanometers or so. This study, I'm only giving you a short snippet of it, also included atom probe and other characterization as well. But for an industrial example of the consequences of what I've just shown you, we can rationalize the high corrosion resistance now for the presently in-service aluminium copper lithium alloys such as 2050, whereby if we look at the evolution of microstructure from the naturally aged condition here right through to the underage condition where we see the evolution of the T1 hardening phase, which is Al2CuLi, through the peak age condition, slightly overage condition, and in the overage condition, we see essentially minimal width increase in the hardening T phase, T1 phase, I should say. And if you look at the T1 phase in a little bit more detail, it doesn't really thicken beyond a couple of unit cells. So the average thickness of T1 precipitates never really thickens beyond the critical width needed to cause pitting corrosion en masse. As we see here in the plot that I show you here, one can compare the average T1 thickness as a function of aging compared to the thresholds that were set by Gupta, Rajiv Gupta and co-workers of about 5 nanometers given by that green line from work on 7000 series alloys, and the orange range that was determined by Kevin Ralston for 2000 series alloys, largely aluminium, copper, magnesium alloys, which shows a range of about 3 to 6 nanometers there. And so you can see we never really get to that critical thickness, and that's a way that we can rationalize the high corrosion resistance that's afforded in this particular alloy. All right, moving on to quasi-in situ STEM, which has really been driven hard in the field of corrosion by Shravan Carey. Here we see an example that reveals that Q phase, which is an aluminium, copper, magnesium, silicon precipitate in 6000 series alloys, which are useful in architectural and automotive and transport applications, also de-alloys. Perhaps not surprise, surprise at this point. What's even more interesting is that when you see what you see in these images shown here is that copper also redeposits back onto the surface, so back onto the surface of Q phase itself, and does so in a manner that shows so-called growth twins, which are often seen in electrodeposition of copper thin films. So there's clearly much happening here that's yet to be fully unraveled. Again, some work of Shravan. Beta phase, which is a magnesium silicide, Mg2Si, also either de-alloys or dissolves incongruently at this very fine length scale, as studied from quasi-in situ STEM. Here we see selective magnesium loss and silicon remaining in an oxidized form of silicon. And this phenomenon, actually I should probably mention, was previously shown at the large length scale, so the micron scale, some years ago now by Siadba Jain on his work with Rudy, I think, on on silicon-rich casting alloys. So look, not just the classic S phase, but everything that we actually now take a closer look at in aluminium alloys, D alloys. One of the coolest things that you'll see in recent work is a paper that comes from the future. Yay! So when I mean future, December this year, and it's some work from Ali Kasari and his great colleagues that employed in situ TEM. So in other words, in situ imaging in the electrolyte. So this is not our work, but this is so exciting that I wanted to share it. And so what you can see here in this snippet of Ali's video, which is amazing, is it shows the evolution of localized corrosion and indeed de-alloying and copper redistribution in real time. I'm not going to add too much more here because this is not my story to tell. This is Ali's story. But I'm very excited, like I know many others are, with the ability to study corrosion in situ because it's very meaningful for everything from allowing accelerated insertion of materials into service to answering some really key questions such as pit transition rules as well. So fantastic work there, and it's great to see the next generation of stars in this area emerging. All right, so look, by way of mini summary, corrosion of aluminium alloys is very much a deterministic process. Essentially, all phases are electrochemically distinct if larger than a few nanometers in their smallest dimension. Also, essentially, all distinct phases undergo some form of de-alloying or incongruent dissolution. And this has actually been true, I don't have the time to present in here, for even so-called cathodic particles and noble constituent particles that not only lead to corrosion of the adjacent matrix, but themselves, while serving as a cathode, undergoing some incongruent dissolutions. So these are all prospects for driving alloy design and microstructural engineering. So I'm going to show a couple of examples that drive home this sort of corrosion metallurgy, so to speak. But it really is a renaissance now, because if you think about the way that these alloys are dissolving and what the surface looks like as it kinetically develops, that's also very, very relevant to protection strategies and targeting corrosion protection strategies. So let us now look at additively manufactured 2024, which is an aluminium copper magnesium alloy prepared here by selective laser melting. Compared to the wrought microstructure, that's well known and includes many constituent particles of appreciable size, in the micron and tens of microns of length scale, and then forming clusters that could often be even 100 microns in size. We have a very different microstructure in the additively manufactured 2024, as you can see here. So the microstructure is very refined. On the nanoscale, we see the hardening phases, and here what we see is the hardening phase is actually a doped aluminium copper phase, not the S phase that's normally seen in wrought 2024 that is associated with dislocations, as you can see here. So the 3D printed 2024 actually has a solidification microstructure, and that reveals to us that the first phase to form upon solidification, which is not S phase, but a theta variant, is retained. The corrosion rates of additively manufactured 2024 are much lower than those of wrought 2024, and this is attributed to the annihilation of constituent particles as localized corrosion sites. Also the refinement of the hardening phase. And look, I'm not going to elaborate here because a deep dive into this work was actually is actually on YouTube from Umaima's presentation at the last ICAA meeting. But I think that's an important example so that we can also start to see sort of a body of evidence emerging. So since then, a similar story rings true for the aluminium zinc magnesium alloy 7075. What we see here when produced by additive manufacturing is a very different nanostructure to the wrought alloy. And here you see the wrought alloy where you see EDA precipitates, so MgZn2 precipitates. What we actually have, however, in the additively manufactured alloy of 7075, in 3D printed 7075, we can see that in all three zone axes from nanobeam diffraction of the same hardening particle, we exhibit twofold, threefold, and fivefold symmetries of an icosahedral quasicrystal. The quasicrystal has a unique magnesium copper zinc composition and has never previously been seen before in terms of either composition or indeed in crystal structure. So shown here close up, we can see the crystal structure, which we've termed new phase, not because it's new as in not seen before, it is that, but it's been named after the Greek letter Ni. All right, so corrosion-wise, we see very low rates of corrosion relative to wrought 7075 when we look at the 3D printed 7075. And here I show the analysis using a post-immersion scanning electron microscopy, where the remarkable thing is that the size of the pits in the 3D printed 7075 are essentially, and in fact always, submicron and superficial in nature, which is quite remarkable. So in using the possibilities from additive manufacturing, we can also cheat solubility limits. And a PhD student that's working at the moment called Abhi Babu has sought to make aluminium alloys that are hyperloaded with solute for the pursuit of ultra-high strength aluminium alloys. So again, here we see unique quasi-crystals forming and a complex nanostructure and the possibility to achieve significant hardness. So why is this important? It's because 3D printing allows us to create these sorts of components in net shape. As you can see here, have a look at how this fabulous sample looks. This is the composition of the alloy you saw in the previous slide. This is net shape printed, high solute, fully dense. So while we admire this image, we've seen that corrosion for aluminium alloys is deterministic, and I think it's probably fair to say that as a community we now get it. That knowledge has largely come from the last couple of decades, but now what's happening, as of today, is we're seeing that things like additive manufacturing can present new phases that we've not seen before, not studied. There's new levels of refinement. We have hyperloaded solutes and the possibility to create alloys that have never been made before in terms of the amount of solute we can add to aluminium, but also in the range and the combination of alloying elements that we can alloy with aluminium. All of these things give us the tools to also engineer for corrosion. Interestingly, like I alluded to just a moment ago, additive manufacturing can also allow alloying with transition metals not previously explored, except for example, some work from the likes of Jerry Frankel over 20 years ago now that studied thin films and showed that addition of elements such as tungsten can dramatically improve the pitting resistance of aluminium, which is marvelous. So look, not much time to cover a lot of things today, but I did want to leave you with a few points, and they may seem trivial, but they're actually quite new points. For aluminium alloys, everything de-alloys. Absolutely, every unique electrochemical entity in an aluminium alloy that we take a closer look at is de-alloying to some extent, whether it's an anode or a cathode. This has ramifications for protection strategies in a post-chrome protection world. For aluminium alloys, everything is actually deterministic, which is both daunting but very useful. There are excellent prospects for designing in durability based on what is now known, and hopefully what took the first 115 years or so of the journey for aluminium alloys need not take another 115 years in terms of alloy development. I think it's probably fair to say that advances in characterization continue to drive understanding when it comes to corrosion of aluminium alloys. And I think that rings true now with some of the work that I showed, particularly the work from Ali over at Delft on the in situ TEM. And the prospects for new alloys is vast and extremely exciting. So examples include aluminium transition metal alloys, net shape, high strength, corrosion resistant aluminium alloys. So there's a lot of work that I've presented here in a very short amount of time, where I've sought to cover the concepts of the relative intensity of corrosion that you get from various particle types. One thing that I didn't get to talk about is grain boundary properties and so forth. A lot of that is covered in the literature, but I really just wanted to give you the summary and prospects as summing up where we are now in the field, and to hopefully be able to elaborate as a community in person at the next ICA. So look, thank you very much for having me here. It's always my pleasure, and we all owe ourselves a trip to France when COVID is over. For those that want to reach out to me, please do anytime. You can find me here anytime whatsoever, and goodbye.